speaker is Gregor Behnke.
I could also use this one. So this is my talk. This is a solution, but is it though, verifying solutions for hierarchical planning problems, which was joint work with Daniel Holler and Susanne Biundo. In classical planning, the problem of plan verification is actually very simple. What you're given is your planning domain, an initial state, a goal state, and a sequence of actions, and the question is this a valid solution for the planning problem you're given? Well, this is linear for classical planning with totally ordered plans. And there is existing software that provides this capability, namely val. In the case of hierarchical planning, where you not only have to check whether you're reaching some state in the end, which might even not exist, but also have to ensure that your plan is a refinement of a given initial abstract task, this problem is not linear but becomes NP-complete, which was shown 2 years ago by us. And so far, no practically usable tool for verifying hierarchical plans existed. First question might one pose is, well, why do we actually want verification tools? Well, the first one is, well, we should validate our planners at some point to be sure that what we are producing are actual solutions. Also, if we ever in the future repeat the IPC1 for hierarchical planning to do another hierarchical planning competition, we need to check whether the solutions produced by the planners are actually solutions. And it also has applications if we want to do something like post-optimization, where we get a plan, change some of the actions, and then we have to ensure again that it is still a solution. And in a similar fashion, when we want to do things like plan repair, something goes wrong, we change the plan and again have to ensure that it is a solution. So what have we done in the paper? Well, we provided a translation of the NP-complete plan verification problem into SAT. This translation needs a bound in the formula construction. We provided succinct means to compute the bound, and we showed that the translation is actually usable in practice. So just to give you a brief reminder of what HTN planning is. In contrast to classical planning, we have two kinds of actions called primitive and compound actions. Primitive actions are the same as in classical planning. Contrary to classical planning, we are not given a goal state to reach, but an initial abstract task to execute. How is this execution defined? Well, by methods, which are mappings from abstract tasks to partially ordered sets of other tasks, either abstract or primitive. And what we are allowed to do is to replace abstract tasks using these methods. For example, in this case, I'm choosing this first method to replace the initial abstract task and to reach a plan that contains this abstract and this primitive task. And I have to repeat this process until I've reached a plan that only contains primitive tasks, because we assume that we cannot execute abstract tasks directly. So repeat this and repeat the process until we've reached a primitive plan, which is still partially ordered, and then to ensure that it's actually a solution, we have to test whether there is one total order of the plan that is actually executable. So what we want to do is, given such a partially ordered set of primitive actions, to determine whether it's a valid solution for the planning problem. And based on the previous slide, we have to do three things for that. First, we have to check whether it's a valid refinement of the initial abstract task. Second, we have to check whether it's primitive, and third, whether it's executable. Checking primitivity is obviously trivial, because you just have to check whether all your actions are in a given set. And in the paper, we also assumed that checking executability in this case is trivial, because in practice, you're usually not given a partially ordered set of primitive actions, but a totally ordered set, and then you could just use val. If you're given a partially ordered set, this again becomes NP-complete, and you have to write a separate solver for that. So what we are concerned with in our paper is to check the refinement property. We're given a totally ordered sequence of primitive actions and have to determine whether they are a valid refinement of the initial abstract task. A witness for this refinement is called a decomposition tree. These are these trees I've shown so far here, which always start with the initial abstract task, and their leaves are the primitive tasks that are contained in the sequence we are given. So just have a look at one of these trees. The first thing we can obviously do is arrange it in layers. So there is a clear first layer, starting with the initial abstract task, a second, a third, and a fourth layer. Then we can arrange also the nodes into positions, starting here with first position. This is the position where the leaf, this is the leaf that represents the first task in the solution. This gets the first position, this gets the second, third, fourth. And we just arrange the abstract task in the middle somewhere above the primitive task. This is obviously always possible. So a solution is then simply a projection of the leaves in the positions onto the solution. And we here assume that in this arrangement, we force actually that no two primitive tasks occur above each other. So this is actually a unique assignment. And what we did was to transform this tree process, this tree here, into a set formula. So we write down a set formula that represents all possible trees of a given height that may lead to a solution, and then just let the Z solver decide whether such a tree exists or not. The nice thing about that is that all the constraints we have to write down are actually local. So there are no real global constraints on this tree. So what we are looking at is one possible node. So in a layer, there are, if I have 5 positions, there are up to 5 nodes in that layer. We're looking just at one of them. What constraints does it have to fulfill? Well, there can be at most one task at that position, not 2. It can only have one parent in the previous layer because it's a tree and not a DAG or something. It cannot contain a task if it does not have a parent, meaning I cannot just invent new tasks and start a second tree. And the most complicated part are actually its children. So if the task is abstract, which is the most general case, I have to select a method for that task, which there can be multiple, but it's just choosing one of them. And I have to choose exactly one of them. I'm not allowed to not choose. Then the method I've chosen produces a set number of subtasks. That's given in the domain. Again, this can vary from method to method I may apply. And then for each of these subtasks produced by the method I've selected, I have to map them it to exactly one of the positions in the next layer. And I have to do that again for all the tasks in the method I've selected, and potentially for all the tasks in all the methods that I may have selected. Then clearly, if I've selected a method, produced its subtask, and assigned the subtask to a position in the next layer, this task becomes, in the tree I'm representing, a child of the red task I'm currently talking about. Next, I also have to represent order. I haven't yet talked about order. So in each layer, I have an additional partial order represented on the tasks in the layer. And whenever I'm choosing a method and mapping tasks to the next layer, I've to ensure that the order that is given in the method is also respected by the task in the next layer I'm mapping to. So if I'm mapping this task to this one in the next layer, this one here, and here's an order, there also has to be an order between these two tasks, and also I have to inherit order, meaning if there is an order between this task here I'm currently talking about and another in the layer, for example, this task here is the child of this one, and this task here is the child of this one, then it will inherit the order. So up to now we have assumed to know how many layers we need. And the problem is, well, in order for the translation to be correct in one run, so we just want to create one set formula, check it once, and take that result as our verification result, we have to determine the k such that if a plan of the given length, so we're given a plan, we know the length of the plan, if a decomposition tree exists, then also one with height less than k exists. And this k will then be the number of layers we're using. The problem is that I'm having this strange construction here is because we can have actual recursion in the domain. So technically for a plan of length n, this height can be infinite. So there can be no upper bound, but we can do clever tricks to reduce recursion and actually give this kind of bound. So what we ideally need to do is to compute a maximum decomposition depth that can lead to any plan of length n. We've developed in total 4 methods to compute this. 3 are already given in the paper. The 4th is new, and I'll just add it for completeness to the presentation here because it's actually better than the 3 we've come up previously. The first method is based on the proof technique we use to show that plan verification for hierarchical planning problems is NP-complete. In that proof, there was a lemma contained which actually computed already this bound by in a theoretical upper approximation, which is 2 times the length of the plan times the number of abstract tasks in the domain plus 1, which doesn't seem that much. But if we're having a look ahead at the empirical evaluation we've done our evaluation on 5 domains, each containing several instances, and for every domain we are just plotting the minimum and maximum k we've computed for all the instances. So for example, for translog, the minimum was 70 and the maximum for all the instances was like 1,500. Even worse for the monodomain, it got up to 11,000. This is just not practically tractable. The formulas you have to construct for these Ks are infeasibly large. The second method centers around the observation, well, if all the methods we have would produce more than at least 2 methods, then we would have the property that if we apply a decomposition, the size of the plan can only grow. So what we can try to do is to eliminate these methods that are bugging us here, which we call unit methods. They're essentially decomposing in one abstract task into one other abstract task. And this can be done by essentially expanding them in the model. And then we can use the length of the plan minus 1 divided by delta here means the size of the smallest method minus 1, which if we have done this is at least 2, meaning we have at most plan minus 1 divided by 1. This leads on most domains to very low, to lower bounds for k. The problem, however, becomes in some domains, this compilation becomes intractable because it can introduce an exponential amount of new methods. And in the monodomain, which already has a lot of methods, this becomes absolutely intractable. So just put infinity here. The third method is based on a graph structure we call task schema transition graph, which is somewhat related to the domain transition graph from classical planning, which is a structure that tells you for 2 abstract tasks whether there is a method decomposing this task leading to another one. You can easily compute this for any planning domain you're given, and then look for acyclicity. If this graph is acyclic, you can apply at most as many decompositions in a row as this graph has as the longest path of this graph is long. So if it's acyclic, we compute the longest path, which is easy, and then just use this approximation for the upper bound, because there cannot be more layers. In every layer you have to apply 1 decomposition, and you can apply at most the length of the path in a row, so the number of layers is absolutely bounded. And interestingly, for most domains, this graph is actually acyclic, except for a few instances in the smartphone domain, and leads to very low bounds. Last observation, it's a new method. Technically, not all unit methods are actually problematic, only those that form what we call a unit cycle. So if you have a cycle of unit methods decomposing into each other, that's problematic. But those can be easily compiled away because these abstract tasks are all identical to each other. You can just replace it by a new abstract task, and then you can apply a dynamic programming scheme to compute for every task and number of actions how many decompositions you need tops to reach that. And then just use the obvious value from the DP you get. And these values can be computed for all the domains, all the time, and are always small. And to sum up, well, in the end we can just use the minimum of all the lines because we have computed a lot of upper bounds and the minimum is always feasible. So what we did in the end was an extensive evaluation containing 4 well-known benchmarking domains for hierarchical planning and 1 domain that was used to create planning instances for HTN planning a domain that was created for creating plan recognition instances. In total, there were 101 planning instances. The characteristics of the domain are given here: number of state fluents, abstract primitive tasks and methods. And again, the table I'm showing here, so there is quite a correlation between this large size of the domain here and the large theoretical K. And from our evaluation, we saw that out of the 101 instances, for 88 of them, the K we computed using these 4 methods was actually exact, meaning 1 K lower, we could not verify the solutions anymore, because the smallest decomposition tree that exists has actually the size K we computed. And just as last slide, these are the runtimes. We've conducted 3 different evaluations. One run on actual solutions. This is the length of the plan we've been verifying, and this is the number of seconds it took to verify the solution. So in most cases, we are well below 200 seconds. Those are potential solutions generated just by random walking of the same length as the solutions we have to verify. Apparently, these are very characteristically non-solutions. And lastly, we've taken the solutions and just swapped one of the actions in the solution, disregarding executability in this point, because we're only looking for the refinement property. And what we're seeing is, yes, we could refute all these solutions, these non-solutions in time, but the time actually grows up to about 100,200 seconds. So what we did, to sum up, was to provide the first working plan verifier for HTN planning, and showed that plan verification is actually possible in practice, as I've shown in the evaluation. And we showed that the necessary height bounds can be derived automatically and that they are actually very succinct in practice. And I think that this also provides a nice and promising direction for future research. First, we can aim at reducing the size of the formula, which is still bicubic in the length of the plan. So this might be an interesting way to look ahead. It also might be interesting to look at specialized formulas for totally ordered problems. Technically, for verification of totally ordered problems, this is trivial because then the problem becomes equivalent to parsing of context-free grammars. But once you have such a formula, you can use it not just as a verification system, but also as an HTN planner itself. Just omit the part of the formula that asserts the actions you're given and replace it by a classical set planning representation, for example, the one by Yossi or by Katz and al. So thank you very much. Any questions?
I think we have time for about one question.
Sorry.
Could you use your bounds in an HTN planner, and if so, how? Aside from your SAT encoding idea here.
Well, in some of them, yes. But using them is set too much. This is, for example, this bound is an absolute bound. You can. There is no way in the HTN planner to go beyond that. What you could do is something like restrictive length search. So you're trying to, instead of just searching through the space of all possible plans, or all possible progressions, you can limit yourself to a given length of the plan. So you're just looking for solutions that contain 10 or less actions. And then you could use these bounds to abort if your decomposition reaches a depth higher than that. Yeah, that would be possible.
Okay, thank you.